Well, hello there. We have another application of derivatives that I want to take a look at. These are linear approximations. Now, one thing that we know is that the derivative can be used to find the tangent line to a curve, but there's one really great use of the tangent line. The tangent line is actually a very good approximation of the curve, so long as you're looking close to that point of tangency. Right here we have a curve and we have a tangent line. And if you were to look anywhere close to where that tangent line touches the curve, those two are very, very close to each other. And the reason that this is helpful is that there are certain circumstances where a linear function, which is what the tangent line is, might be easier to work with than the function itself, especially if we just need an approximation. So let's go through this a little bit more formally, and I can show you what I mean. So let's suppose we have a function y equals some function of x, and we want to find the tangent line specifically when x equals a. Now, there's a couple of things that we know about that tangent line. Specifically, it contains the point a comma f of a, because we know it's a tangent line at a, and when x is a, y is f of a, so that's the point of tangency. And we also know the slope of the tangent line. That comes from the derivative of the function at that value a. And if we know a point and a slope of a line, we can get an equation of that line. We can put this into point-slope form. You'll remember point-slope form is y minus y1 equals m times x minus x1. The y value of the point is f of a. The slope is f prime of a. And x sub 1 is just equal to a. And we add f of a to both sides to get y alone. That gives us y equals f of a plus f prime of a times x minus a. This is the equation of the tangent line to the curve at the point x equals a. And since this is a good approximation for our function near x equals a, we can say that our function near x equals a is approximately equal to f of a plus f prime of a times x minus a. And again, this is near x equals a. This is a linear approximation. You could even write this L of x as in the linear approximation of x equals f of a plus f prime of a times x minus a. Now, I know that's a lot of notation and a lot of very similarly written things, and you're probably wondering, where might we use this? And I have a really great example. We want to find the linearization of the function f of x equals the square root of x at a equals 1, and use it to approximate the square root of 0.97 and the square root of 1.02. Now, of course, if we have a calculator, we can just plug those in and get those approximations. But let's pretend we don't have a calculator, or let's pretend that we lived before we had electric calculators. And let's see what this gives us. So to find the linearization, we're going to need the derivative evaluated at that value. And so the derivative of the square root of x That's the same as x to the 1/2. The derivative of that is 1/2 x to the negative 1/2, or 1 over 2 root x. And we want to evaluate this at a equals 1. So we want the derivative at 1. That's going to be 1 over 2 root 1, which is 1/2. So f prime of 1 is 1/2. We're also going to need f of 1. And of course, f of 1 is just the square root of 1, which is 1. So we can use that to get our linearization here. The linearization is given by f of 1, which is 1, plus f prime, which is 1/2, times x minus a, which is 1. And we can distribute that 1/2, so it's going to be 1/2 x minus 1/2. And if we want, we can put this in slope-intercept form, 1/2 x, and then 1 minus 1/2 is 1/2. So our linearization is 1/2 x plus 1/2. And so in particular, if we want to know the square root of 0.97, approximately, we can plug that in to this linearization since 0.97 is near 1. So that's going to be 0.97 halves plus 1/2. And that's going to be 0.485 plus 0.5, which is 0.985. And so that tells us that the square root of 0.97 is approximately equal to 0.985. And if we remember that we are in the 21st century and we use a calculator, the actual approximation we get is 0.984887 ... And we can see this is a pretty good approximation. It is correct to the nearest thousandth. So this ends up being very, very useful. Let's try this for the other approximation. We've got the square root of 1.02. That's approximately 1.02 halves plus 1/2. And that's going to be 0.501 plus 0.5. So it's going to be 1.001. And that tells us that the square root of 1.02 is approximately equal to 1.001. And when we use a calculator, we get 1.009950. And again, this is correct to the nearest thousandth. Now, really quickly, I want to explain that we're not always going to get approximations that are that good. In fact, for this particular problem that we just did, since we picked a equals 1, this is only going to be very accurate if we're picking square roots of numbers that are very close to 1. If we tried to use this linearization and we picked a number like the square root of 7.25, 7.25 is nowhere near 1, and so this is not going to give us a good approximation at all. It's going to be wildly inaccurate. And even if we picked a different value of a, we're going to run into some issues here because we don't know any numbers that are perfect squares that are close to 7.25. This example that we did worked really well because the numbers we picked were really close to a perfect square that we could easily evaluate. But if we're trying to evaluate something that's not near a perfect square, it becomes a much more difficult thing to do. So anyways, I just wanted to show this to you because this ends up being a nice application. We get an insight into how we might be able to calculate certain values. And in Calc 2, you're going to see some ways using different types of infinite series that we can come up with approximations for certain values of different functions that are difficult to evaluate without a calculator. For example, different values of e to the x or different values of sine, cosine, tangent, where they aren't super simple values where we happen to know what the sign of it is, like sine of pi halves or something like that. So these sorts of things end up being really interesting moving down the line.